If I drop this blueberry somewhere in the center of this stadium, do you think you could find it? This place is pretty big. That blueberry is pretty small. But consider this. If we took a single atom and expanded it to the size of this stadium, virtually all of its mass would exist right in the center, and is space pretty much the size of that blueberry. The scale of atomic structures is wild. This is real CHEM. Have you seen this kind of image of an atom before? An iconic graphic from the 1950s. It shows some electrons circling around a nucleus. Well, it remains kind of right. But as well as some of the structural detail, what is really missing is the scale. If our blueberry represents the nucleus, the rest of the atom is as big as this entire stadium. Mostly empty, but occasionally occupied by electrons carving out space around the nucleus. But it's not just the space we need to consider. It's also the mass. Nearly all the mass resides in this tiny blueberry nucleus in the middle. Strip away the cloud of electrons that surround it, and the mass would pretty much be the same. In real terms, just think what that actually means. This stadium weighs, say, maybe 250,000 tons? Yet virtually all of that mass is held just in these tiny spaces at the heart of each atom. But those electrons still matter. Without them to hold this nucleus apart from other nuclei out there, this entire structure would just collapse into a tiny ball of nuclear matter. In atoms, although the mass resides in this little blueberry nucleus, it is the size of the electron cloud surrounding the nucleus that actually sets the size of the atom. A more massive nucleus leads to larger atoms, but not because of the mass or the size of the nucleus. Instead, it's a result of the charge. A bigger positive charge in the nucleus means more electrons. To see how the number of electrons in an atom influences its size, let's consider electrons as occupying the seats in the stadium. The seats often fill from the front outwards. Well, electrons located around a nucleus follow a similar tendency. As we add electrons to an atom, the electrons have to move out to further and further distances from the nucleus. But it is those outermost electrons that dictate how this atom interacts with everything around it. Atoms of one element react with atoms of another element to form compounds, which in turn produce the seemingly infinite number of substances. The interactions of those outer electrons really count. And so, we need to understand and be able to predict their behavior. A blueberry in the stadium is perhaps a good way to remember atomic structure. But it's not half as incredible as reality. This unit, we unpack the journey of the atom. We look at atomic structure in detail and the story of how it was understood. We then go on to look at common forms of matter when atoms come together, ionic and molecular compounds. On your journey through this unit, don't lose sight of the wonder of what we are dealing with. So let's get to work. This is Real CHEM.